Today we're going to talk about an alternative way to find a particular solution to a non-homogeneous second-order differential equation. Now we have the method of undetermined coefficients, but every once in a while you'll run across a second-order differential equation to which this method cannot be applied. For example, in this thought exercise, I've given you two second-order differential equations. I claim that method of undetermined coefficients cannot be used in either one of these situations. Why do you think that is? Why do you think method of undetermined coefficients cannot be used for the ODEs that are listed here? The issue with the first equation is that we had a little bit of fine print when we were using the method of undetermined coefficients. The method could only be used when the differential equation had constant coefficients. And this one does not have constant coefficients. This equation in A is a Cauchy-Euler equation, not an equation with constant coefficients, and therefore method of undetermined coefficients cannot be applied to the equation in part A. The issue in part B is that the function f of x on the right side does not correspond to any entry in our guessing chart. You can try to guess an equation of the form maybe some constant times the natural log, but it's not guaranteed to actually work out. So in situations like the equation in A or the equation in B, when method of undetermined coefficients cannot be used for whatever reason, we have a new technique which is called a variation of parameters. Now, warning, in order to use variation of parameters, this is one of those formulas, like the reduction of order formula, that requires y double prime to stand alone. Okay. Now, to use the variation of parameters technique, you need to start by finding your complementary function. You need to start by finding two linearly independent solutions to the complementary equation. Let's just call them y1 and y2. Then you're going to need to calculate the Wronskian for those two solutions. So that would be the determinant of the 2 by 2 matrix, which has those two functions in the top row and their derivatives in the second row. Let's call this W for short. Now, once you've calculated W, use the following formulas to calculate the values of two other functions. We're going to call those other functions U1 and U2. The formulas that you need are that if you take U1 prime, that's going to be equal to negative y2, y2 being your second linearly independent function, times f of x being the function on the far right side of your ODE, f of x, and divide that quantity by the Wronskian that you calculated in step number 2. You calculate the second function by using the formula u sub 2 prime is similar but no negative sign, positive y1 times f of x divided by the Wronskian. Set up these formulas and then integrate to find the functions u1 and u2. Finally, once you've done these three steps, you can assemble a particular solution. the particular solution is given by y sub p is equal to u1 times y1 plus u2 times y2. So fairly similar in spirit to the reduction of order formula. In the reduction of order formula, you had one solution y1, and you multiplied y1 by some function u1 to get the second solution y2. In variation of parameters, you have two solutions to the complementary equation, and you're multiplying those by functions and adding them together to build up a particular solution. Now there is a proof, there is a derivation of this formula. I have decided not to show you the derivation of the formula because I'm not sure if it's the best use of time. If you're interested in that, it is in our textbook, and also feel free to ask me about it. To demonstrate the method, let's go ahead and let's solve y double prime plus y equals cos squared of x. So the first thing that we're going to need to do anytime we're finding a general solution to a non-homogeneous ODE is we need to find the complementary function. So I'm going to replace the right-hand side with 0. This has constant coefficients, so I'm going to go ahead and set y equal e to the rx, which gets me x squared plus 1 equals 0, which gets me r squared is equal to minus 1, so r is equal to plus or minus I. Our two solutions are y1 equals cosine of x, and y2 equals sine of x. And that gives me the complementary function c1 times cos plus c2 times sine. Next, we need to find a particular solution. Now, scrolling back up to our differential equation, I suppose it would theoretically be possible to use the method of undetermined coefficients, because the equation, the left-hand side of the equation has constant coefficients, and the right-hand side has the form trigonometric multiplied by trigonometric. But I think in this case, method of undetermined coefficients is going to be a huge pain. Our guess is going to be complicated a lot by the fact that both cosine and sine themselves are already complementary solutions. So you would have to take that guess and multiply it by an x, and you would need to do a lot of product rule when you were plugging that guess into your differential equation to find out what the constants are. So that just looks like it's going to be a pain in this case. And that's why here I'm going to choose to use variation of parameters instead. So to that end, let's go ahead and find the Wronskian of the two functions, y1 and y2, the two independent complementary solutions that we found in the first step. So we have the two functions, cos and sine, written in order. And then we have their two derivatives. If I calculate the determinant of that matrix, I get cos squared plus sine squared, which can be simplified actually just to 1. Now, having obtained the Wronskian, the next thing that we need to do is we need to find the identities of the functions nicknamed u sub 1 and u sub 2, using the formula that u sub 1 prime is equal to negative y2 times f of x divided by the Wronskian. Now, y sub 2 we found in the previous step was given by sine of x. The Wronskian we found was 1. So now we just have to figure out what is the function called f of x in our problem. So I'm going to check, first of all, to make sure that my differential equation is written in the right format. Y double prime stands alone. And since that is in fact true, the function f of x on the far right side is the one that we need for our formula. So this implies that u1 itself is an integral of negative sine x cos squared dx, which is given by 1/3 cos cubed x. And I'm just going to go ahead and find the simplest possible antiderivative. Similar to reduction of order, similar to when we did integrating factors, we only really need one possible non-constant u. So I'm going to pick the simplest antiderivative, the one where the plus c is just equal to 0. So next, let's find u sub 2 using the formula that u2 prime will be equal to y1 with no negative sign multiplied by f of x divided by the Wronskian. And our y1 was cosine. So in order to calculate u2, we need to integrate cos cubed. This can be done using a trig identity. Cosine cubed is the same thing as cosine times 1 minus sine squared by the Pythagorean identity. So I'm integrating cosine and cosine times sine squared. The integral of cosine is just sine, and the integral of cos sine squared is 1/3 sine cubed, using u substitution. So now I can construct my particular solution. The particular solution is given by u1 times y1 plus u2 times y2. Now u1 was equal to 1/3 cos cubed, and y1 was equal to cosine. u2 we found was sine x minus 1/3 sine cubed, and y2 was equal to sine. So after a little bit of simplification, we find that our particular solution can be written in the form 1/3 cosine 4x plus sine squared x minus 1/3 sine to the 4th power. Now this can be simplified a little bit. I don't think that I will. I'm not sure that it's beneficial really to simplify it at this point. But there is a way to simplify this expression using some trig identities. So with that, let's assemble that into our general solution. Y is going to be equal to our complementary function, c1 cos plus c2 sine, plus the particular solution that we found by a variation of parameters, cos to the 4th power minus 1/3 sine to the 4th power plus sine squared. That is how we would use variation of parameters to find one particular solution to a differential equation, if either method of undetermined coefficients is not possible, or if it just seemed like using that method is going to be a big pain. Let's do a similar example, y double prime plus y. This time let's let it be equal to secant. And we're going to begin, of course, by investigating the homogeneous version of this equation. But the homogeneous version of this equation is exactly the same thing it was in the previous exercise. So just borrowing that work, we already know that two complementary solutions are given by cosine and sine, and therefore the complementary function is given by c1 cos plus c2 sine. Now let's begin the real work of finding the particular solution. And since the y1 and y2 have not changed, then the Wronskian will also be unchanged. It's still going to simplify just to 1. So our u1 prime will satisfy the equation negative y2 divided by the Wronskian multiplied by the function f of x on the far right. Now let me check y double prime stands alone. So the differential equation is in the correct format, and f of x is exactly equal to this function secant on the right side. So u1 prime is equal to negative sine divided by cosine, and if I integrate that, then I get the natural log of absolute value of cosine. So looking now to u2 prime, u2 prime would be equal to y1, our first complementary function, multiplied by f of x, the function on the far right, divided by the Wronskian, this time with no minus sign, which simplifies to the constant 1, which means that u2 is going to be equal to, I'll just take the simplest antiderivative, x. So what's our particular solution? u1, which was natural log absolute value of cos, multiplied by y1, which was cos, plus u2, which was x, multiplied by y2, which was sine. And now we can assemble our general solution. The general solution is that y must be equal to our complementary function plus our particular solution. That concludes today's material. We introduced an alternative technique that can be used to find a particular solution to a non-homogeneous ODE, which can be used in any situation where method of undetermined coefficients fails or seems difficult. For variation of parameters, the most difficult step, generally speaking, is integrating the expression that we need to find u2 and u1. Integrals needed to find u1 and u2 can sometimes get pretty difficult and require a lot of integration skill. So that's the reason why we don't just use variation of parameters at all times.